you can see in the title, it's a convolutional autoencoder, and here we already covered the materials for autoencoders. I mean, this kind of bottleneck structures for I would say dimension reductions. And at that time, if you remember, it was a kind of based on the ANN structures. And if you think about, we learned the convolutions and the convolutional neural net, we learned CNN. So the question is, what if we have inputs as image as inputs and outputs, and we want to do dimension reductions? Then probably you can think of how do you combine the convolutions and convolutional operations with the autoencoder. That is the topic for the CAE, and we can extend it to FCN, which is fully convolutional neural net. It's going to be the next topic. So as a motivations and the convolutional autoencoder, so the motivation is, what about if we feed image to autoencoder? So you can think of as this one is AE, and probably you can see, say we have images, and here probably reconstructed image, and this is like, again, it's kind of autoencoder structures in two-dimensional space. That's the only difference that we have. And probably the values over here, it will be same as you can think of as features, the key features in a given inputs images that we have. Right, I mean, I think it's a natural way that you can think, and you can extend it, how do you combine the convolutions or CNN with the autoencoder. And you can think of over here, it's decodings, and over here, this is decode, and over here is encode. Or you can always downsamplings, and it's upsamplings. And we did this way, this in downsamplings or the decoding part of CA is same as CNN. And the only difference is that how you do upsamplings, there will be the key, the structures that we need to study for convolutional autoencoder. And you can think of as here it's convolutions. We will do convolution, and we don't know what it is for upsamplings, but in conceptual it will be the opposite of convolutions, right? So in order to reconstruct it from the features to the image, or reconstructed it, so you can think of as a deconvolutions or decomp, but actually it's not. So I'm going to explain it, but here in convolutional autoencoder community said it's a transposed convolution layers. That's what these things. Okay. So actually, you don't have to implement the convolutions and the opposite of convolutions if you use a TensorFlow, right? So TF dot NN dot conv to D. So we know that if you just take a look at these animations, so the input is the 4x4, and with these two options that we have, I think is now you know that it's padding. We have valid options and the same. Right, it's whether it's gonna tell tell us that whether we do the zero paddings or not, and stride, right? I mean, just take a look at the animations over here. It's basically these two are the key. So this one is for the batch, and the other one is in the channels, and these are the height and weight. I mean the width and height. So it's a 1x1 stride. Let's see. Right, these the options that we need to tell, or we need to define it. So there's paddings and stride. In convolution. And another example that here is it's the same stride. If you have paddings, then padding is the same. Here in the original image, the size is 5x5, and we did paddings. The output same as 5x5. So having the options, we keep the input and outputs before and after the convolutions. The size of the images we keep the same. In order to keep the same, we need these zero paddings. So that's what's happening inside. And for stride, as you can see, I just kept for paddings, I just said it the same. If I have stride like that, just take a look at the animations and see the difference. So over there, it's a two-step jump in that direction as well. So over there, the output is 5x5. Over there is here just focusing on what's the size of input and what would be the size of the outputs. That's the key. So having this, it's over there we do downsamplings. And if you go back to previous one, over here is downsamplings. You can play with the optional paddings and play with the stride to get the downstream the images that's smaller than the upstream images. Now, from this one, the next now what we want to do is we want to do opposite of conv 2D, right? So in that case, I want something like this input and outputs. So I need to reverse the input and outputs. So if this is inputs and outputs, as you can see over there, is we do upsamplings. That's in conceptual wise, that's it will be the opposite of conv 2D, but there's no such operations. So instead of that, we have conv 2D underbar transpose. Don't worry about the name of transpose, and just there is a reason for the naming as a transpose, but in this lectures, don't worry about it and just read that, and probably you can think of it as a deconvolutions or opposite way of convolutions. That's okay. And here, this is the input, and this is the output, and the size of is 2x2, and the output is 4x4. We are doing convolutions, right? We did a lot of zero paddings. So, and in that directions, we do convolutions. And as you can see, it's upsamplings. Okay, so just don't worry about what kind of the operations in the conv 2D underbar transpose. just looking at the input and outputs, and you can see if you do these kind of operations, the output side, the image of the size of the outputs or the output image is now it's in the upsampled. Another way that we can do is that here for in the previous one, the stripe is one by one. In the next, for transpose it in over there, if you look at the animations, it's again is in stride. In conv2D sense, it's one by one. But in conv2D underbar transpose, the definition of a stride is really different. Over there, these are the definition of a stride. So as you can see, it was in the original image was 2 by 2, but in over there is 2 by 2. It's kind of split them. And in given image like that, now I split it like from that and do convolutions. Then over here, input size is 2 by 2, the output size is 5 by 5. And from here, what eventually what we got is upsampled. Okay. And again, it's the 3 by 3, and we will get 5 by 5 for like that. So what we, in order to, to implement the CAE, convolutional autoencoders, the idea is that here is fully convolutional. There's no flattening part, because remember in CNN structures over there at the end, we do like over here is fully connected network. Now we don't have this. All the process, it's convolutions. So we call it fully convolutions. There's no dense layers that I use. And one thing that I want to mention here I use decomp, but it's not deconvolutions. You use the convolution, transpose convolutions, but I use the decomp. And the naming it, I mean, inputs and the conv1 and conv2 and conv3. And in 1, 2, 3, and 3, 2, 1, I number in the opposite way. And here is again, it's fully convolutionless, and there's no dense layers. And for again for the MNIST data set, starting from 28 by 28, since this is we're dealing with the images, the output should be the same size. I want to reconstruct it. Okay. Now I'm using the up to this point, it's the same as the convolutions. And 14 by 14 with the 32 channels or corners, and 7 by 7 and 64 corners or channels that we have at the end, because I want here, now this is like 2 node. Remember in AE structures, I use two hidden layers. I mean the 2 hidden states as a latent space. So in order to make these 2 are the same, I use from here I'll do transpose convolutions and transpose convolutions again to 7 by 7 and 14 by 14 and 20 by 28 by 28. We constructed it. So I want to know how good in terms of reconstruction errors, and I want to know what's the physical or here in latent space. In this case, is two variables. That's the structures that I want to implement it and to see. Here, input and the first convolution layers and second convolution layers. Then at the end, we got over here. And for deconvolutions or transposed convolutions, here, look, the size. Okay. And the corner size, things like that. And for the weights and bias, I mean, same. And one thing that you should notice it is here convolution same as looking at the first corner h and width, second corners and third over here. This is input and output channels for conv1, and this is the input and outputs for the conv2, and input and outputs conv3, right? And for this guy, one thing that you should let me see, like that, right? Like this. For this guy is actually the input side, and that is the output side. So you have to flip it. That's the kind of the that I find out that you guys have made. And over there is you made a lot of mistakes. So how do I say? Actually, over there it's over there is the convolution 3, but when you plug into over there, you have to do you have to swap it. Okay, make sure this part and this part is be careful. You made a lot of, I found that students made a lot of mistakes on that. And for encoders, same as previous one. For decoders, here, the only difference is that instead of conv2d, you have to type it or use conv2d underbar transpose. So that way that the TensorFlow is recognized that we are doing upsampling. Okay. Then up here we use tf.nn, and there's another options that tf.layers. It's much easier to use that. So there's, I mean, another options. And tf.layers and things like that. And we have tf.layers that come to the transpose. Now, like, you don't have to worry about any, like, it's much easier to implement it. Now, when you train them and the reconstructions, if this is the inputs and will be the output as a reconstructed image, and you can plot it over here to see what kind of latent space that you have. So using that, let me do CAE. Basically, I mean, these are because I'm using only two latent variables or states, so I can visualize, I can plot it, and I would say it's Z1 and Z2. And they will be the latent space, and as you can see over there, I'm using only like 1, 5, 6 handwritten digits, and in the latent space with only two variables, I can kind of group them like this. And of course, I mean, like what I did in autoencoders, with any the new data points, we can reconstruct it in order to generate the fake image like that. So another one is using the tf.layers. Just repeat it. Actually, the reason that I introduced the CAE, because I want to do this guy. It's a fully convolutional network. So we call it FCN. There is no dense layer inside, and I'm gonna tell you in a minute what it is, what FCN does. And let's review some of the materials that we covered or is dealing with the computer visions, and we do a lot of CNNs for basically a lot of applications for a lot of classifications. But some of the applications in the computer vision, the communities, segmentations. So let me explain what the segmentation is in this slide. So this one is a little different from classifications. So segmentation task is a little different from the classification task. Okay. I mean, let's take a look at this image. We have dog and cat. Right? If the CNN probably we had we first the CNN structures tell whether we have this image or cat or dog. But what we really want to do is that in here it's dog, and over there it's a cat, and the rest of them is a background. That's what actually like a lot of people want to do. So we called it segmentations. And what it does is actually we require predicted class for each pixel in the input image. What do you mean by that? So in these pixels assigned to dog, and these pixels assigned to background. Over there, this pixel is cat. So basically, if we want to do this kind of things, that means we have to do classifications for each pixel, right? So basically it's much harder problems than classification. And another way they want to say is a segment image into reason with the different semantic categories. So in each pixels, we have to assign the labels, and we have to predict object as well. So that's segmentations in general. So again, it's different from classifications, and you can think of as a segmentation is you can think of as a classification problems of each pixel. And classification needs to understand what's in the input, right? Whether we have in the input image where we have to tell whether it's cat or dog or whatever. But for segmentation problems, we have segmentation needs to the not only what is in the inputs but also where, because we have to tell each object and in the pixel wise. So what's in the inputs? and as well as in their locations. So in the FCN it's a fully convolutional neural net. Is being used for semantic segmentations. So I didn't explain what it is, but it's a convolutional neural net to transform the image pixel to pixel categorize. Yeah. So it's all convolutional layers with downsamplings and upsamplings, and given the position on the spatial dimensions, the output of the channel dimension will be category prediction of pixel corresponding to locations. I mean, you don't have to worry about this point. I want to explain it in the following slides. So here you can think of as a like CAE. We do CNN and the convolutions and transpose to get it. And there will be the input image. There will be the output image. When you train the FCN structures, we have to know this one is the labeled. We have to label it like that. So let's think about let's move from the CAE to FCN structures. And let me see. So this one is two, I mean here, okay, let's do. This one is CAE. Based on, I mean, on top of the CAE structures, if you add this kind of skip connections, that's FCN. Because remember over there, it's just dimension reductions, or indeed here from input and outputs we have to know the locations as well. So having this kind of structures is not over there. It's difficult. Having this CAE structures is difficult to memorize or the location informations. That's why we kind of get bypass to get a hint of the locations from. Let me say that again. Without skip connections here, over there it's upsamplings, right? From the low dimensional information to the space, we have to increase or we have to get the higher dimensions. But in the information wise or context wise, it's okay. But if you think about how to reconstruct the locations, but I mean, these are kind of symmetric structures. So I want to get the location informations by having skip connections over there. It's another skip connections. That's the only difference between the CAE and fully convolutional neural net. And again, because we are using skip connections, this is the slide that I mentioned it in. It's a connection bypass at least one layers, and if it's being used to transfer the local transform informations from downsamplings to upsampling path. And this is skip connection. So let's see FCN structures. To obtain the segmentation map, so we need two parts. One is downsampling path and another one is upsamplings. So in downsamplings, in the capture the semantic or the contextual informations, and for upsamplings we have to recover this spatial information as well. So again, it's all about what and where. It's a classifications, and this is segmentations. We have to use skip connections to recover the location as well. So this is the most famous examples for segmentation problems. And if this is let's think about the autonomous vehicle or self-driving vehicles, you have to know, so probably this will be the input image that your car is receiving it in real time. And the first thing is you have to recognize which one is or which one is not. Say is background. You have to recognize which one is the road so that your vehicle can go or is allowed to go and not allowed to go. And it's a binary classifications. For each pixels, you have to say, I'm gonna say this is 1 and this is 0. And from this input image, what that you have to perceive is that you have to say these are zeros and these pixels over there it's 1. It's again, it's the binary classification problems for each pixel. That's what I'm kept saying that. The segmentation problem. So again, it's a binary segmentation problem. Actually, you have two outputs. You can think of it as a one-hot encodings, and I mean these are just, if this is, we say if over there it says road and it's a background. Over is 1. I mean it's 1 and zeros, and over there this is 1 and zeros. You guys know what I'm, because we are doing one-hot encodings. I mean, these are having the same amount of information. There's no difference, but over here we have two layers because we have two segmented images, or how I say labeled. You guys know what, right? So for FCN architectures, having this kind of image, we do CNN downsamplings and we do upsamplings and have, as you can see, skip connections. And the output image, actually we have right there is we have 2, because it's a one-hot encodings binary classification. The size should be the same as the input and output because we have to classify for each pixel. And we want to recognize these the road that we allowed to go. What we can do, and here I'm gonna fix it. It's again, it's from here. It's kind of, as you see, learning from the transfer learnings. It's probably, I will take it in the pre-trained, the weights and structures and weight and bias from the pre-trained networks. And for over there, we're gonna train it. So you can see again, we get it from VGC16s, and for this part, all of them are constant. And for this is the structures, same as CNS structure. For trained, now it's conv6, and over there it's like 4, 3, 2, 1 and output, and over there is it's a transposed and transposed and transposed. And because we have skip connections, that's the how I implement the skip connections. And I hope you all like practice the residual net. So it's being used in the resonant. I think I already explained how to. This is how we implement the skip connections in general. Using that one, and this is the result that I got. Using this image, like the green things are the segmented, and the FCN is gonna tell us that they believe that it's wrong. So you can have you have to drive over there, not in that side.